All right, let's dive right into this explainer. Today, we're going to demystify the complex chemistry of our atmosphere and meet the unseen hero that's constantly protecting our planet. If you've ever looked up at the sky and wondered exactly how Earth defends itself from the absolute extremes of space, well, you're in the perfect place. We're taking an environmental engineering approach to crack open a really critical piece of our atmospheric puzzle, the ozone layer. We're going to break down in really simple terms what it is, how human-made chemicals put it in serious danger, and how global engineering and policy actually stepped up to fix it. Here is our roadmap for today. We'll start by comparing good versus bad ozone. Check out Earth's sunscreen. Explain ozone-depleting substances and how they actually work. Look at the very real dangers of UV radiation. And finally, talk about how we're fixing the hole. Okay, Section 1. Good ozone versus bad ozone. Let's understand the difference. So in environmental engineering, location is literally everything. We have to make a clear distinction here. When we talk about bad ozone, we mean tropospheric ozone, the stuff right down here at ground level. That's a dangerous pollutant born from vehicle exhaust and industrial emissions mixing with sunlight to create that brownish smog we all hate. It's terrible for our lungs and it damages plants. But if you travel 10 to 50 kilometers straight up into the stratosphere, you hit the good ozone. This is the crucial protective shield we're focusing on today. Same molecule, completely different role. Moving on to Section 2, Earth's ultimate sunscreen, the stratospheric layer. You know, it's honestly fascinating that something so incredibly rare carries the weight of protecting all life on Earth. We're talking about O3, a highly reactive trace gas made of just 3 oxygen atoms. Just to put its scarcity into perspective, for every 10 million molecules of air up there, you're only going to find about 3 molecules of ozone. Just 3. Yet this tiny, microscopic concentration is perfectly designed by nature to do one very specific, very vital job. Think of this super thin layer as the ultimate heavy-duty SPF for the whole planet. It works tirelessly to block out roughly 98% of the sun's damaging UV radiation, specifically UVB rays, before it can ever reach the surface. Without this incredibly fragile shield of O3 molecules floating way above our heads, the Earth's surface would just be continuously sterilized by solar radiation. It is, no exaggeration, a matter of life and death for our ecosystems. Which brings us to Section 3, ozone-depleting substances explained, the villains of our story. Back in the mid-20th century, chemists developed what they thought were miracle compounds. They were stable, non-toxic, and seemingly perfect for industrial use. We call these ozone-depleting substances, or ODS. They're packed with chlorine and bromine, and historically, they were in everything. We're talking refrigerants in your AC, halons in fire extinguishers, aerosol hairsprays, you name it. The most famous ones are chlorofluorocarbons, CFCs. The problem is they are so remarkably stable and lightweight that when they leak, they don't break down or wash away in the rain. They just slowly drift upwards, taking years to eventually hit the stratosphere. Now, here's a really interesting twist. The famous ozone hole over Antarctica, it's not actually an empty void like a hole in a bucket. It's a dangerously thin patch of the ozone layer. But wait, almost 90% of CFCs were emitted in the northern hemisphere by industrialized nations. So why is the hole way down at the South Pole? Well, it's all about the extreme cold. During the pitch-black polar winter, a massive vortex forms. This creates polar stratospheric clouds, which act like the perfect staging ground for chemical reactions. As soon as the spring sunlight finally hits, those trapped CFCs rapidly convert into highly destructive chemicals. Let's look closely at that reaction in Section 4, how ozone depletion happens, the chemistry. So let's break down the exact mechanism here. Step 1, that CFC molecule finally floats high enough to get blasted by direct, unfiltered UV radiation. The radiation is so intense, it literally shatters the CFC. Step 2, this releases a free, highly reactive chlorine atom. Step 3, this rogue chlorine atom crashes into a peaceful O3 ozone molecule and violently rips one oxygen atom right off of it. What's left is just standard O2 oxygen. The ozone molecule is dead. The shield is broken. But actually, it gets so much worse because it's a catalytic cycle. The chlorine doesn't just destroy one ozone molecule and call it a day. After it rips off that oxygen atom to form chlorine monoxide, it eventually bumps into another free oxygen atom. That new atom steals the oxygen back, forming O2, and, here's the kicker, frees that original chlorine atom all over again. It's a brutal chain reaction. A single chlorine atom can survive in the stratosphere for decades, tearing apart hundreds of thousands of ozone molecules in this endless loop. And what happens when that shield drops? Section 5, The dangers of UV radiation and the environmental impacts. The cascading effects of losing our UV shield are just staggering. For us humans, it means massive spikes in cataracts and skin cancer. But looking at the bigger picture, the environmental engineering perspective shows a terrifying domino effect. Excess UVB radiation penetrates the ocean and literally kills off marine phytoplankton. Why is that a big deal? Because those tiny microscopic plants consume a massive portion of the world's carbon dioxide. If they die off, they stop absorbing CO2. That leaves more CO2 in the atmosphere, which directly accelerates global warming. It's crazy to think about, but ozone depletion actually acts as a multiplier for climate change. Thankfully, there's a flip side to this. Section 6, fixing the ozone hole through engineering and policy solutions. This is where the story turns into a massive triumph. When the scientific community realized what was happening, the world actually came together to fix it. Engineers had to figure out how to replace these highly destructive chemicals fast. We use a metric called ozone depletion potential, or ODP, where a standard CFC is our baseline of 1. Look at Halon 1301, used in fire protection. It has an ODP of 16. That is terribly destructive. Through clever policies like emission trading, engineers were pushed to replace chemicals like that with HCFCs, which have an ODP of just 0.04. That tiny shift represents a monumental drop in environmental damage. And honestly, this right here is probably my absolute favorite takeaway from all of this. The atmosphere actually has a built-in mechanism to heal itself. Ozone isn't some finite fossil fuel that we're permanently burning through. It's constantly being created by natural reactions between sunlight and standard oxygen. As long as we stop releasing the halogens, the chlorine and bromine that destroy it faster than it can form, the stratosphere naturally reestablishes its balance. Our planet wants to heal. We literally just have to get out of its way. And getting out of the way is exactly what we did. Tracing this timeline, the turning point was the 1989 Montreal Protocol. It's widely considered the single most successful international environmental agreement in human history. It laid out a global phase-out of the absolute worst ozone-depleting substances. Because every nation stepped up, the levels of destructive chlorine in our atmosphere are actively falling today, and the hole is successfully shrinking. Now, scientists estimate it will take roughly 50 years from the peak levels for atmospheric chlorine to fully return to its natural state. 50 years to patch the sky. Which leaves us with a pretty provocative question, don't you think? If the entire world could successfully come together, change course, and engineer our way out of a global crisis in half a century, what other major environmental threats are we capable of solving next? The blueprint is right here. Thanks so much for diving into this explainer with me today, and keep looking up.